I want to start off with this topic. Well, actually, before I start, right, I know some of you guys already have some background information about what complex numbers might involve. You might have looked through the notes, you might have even had to go at some of the problems. But I kind of want to talk about and spend some time looking at the intuition and rationale behind it, because you were talking to me a bit before about this, and it doesn't seem like there is any. Is that the impression that I was getting, or?
What's the impression? I mean, I can understand the laws, but I don't know why the laws are there.
Yeah, so what's the point?
Why is I squared minus 1?
Right, okay. So again, like you already know a lot of this stuff, like a lot of these definitions, the arithmetic, and you're finding that you can actually do a lot of these problems. But as you're doing it, you might be thinking to yourself, hang on, yeah, like what is the point? Why bother doing that? And I think it is important when you start a new topic, there should be some kind of understanding about where this fits in to the knowledge we have already. So let's start with that. Let's talk about the knowledge we have already. When we first started with mathematics, what was like the first thing you learned how to do?
Addition.
Yeah, addition? Yep. Actually, even before that, you might be so count, like literally counting. Right? This is how all mathematics starts. When we talk about numbers, we talk about equations. So we talk about counting things, right? So numbers like 0, 1, 2, 3, and so on, right? These actually belong to a set of numbers. We call them the natural numbers. And we use the capital N to represent this set of numbers, okay? Where does this kind of come up? Well, if we go back to the story of John and Betty, right? John and Betty are two people, and they're discovering all these different kinds of numbers, yeah. And they're great little drawings. I'll try and replicate them. We've got two people here, right? John and Betty. Nice. And what were they trying to do? The first situation was they had some cookies. I think they had like 10 of them, right? And they said, how do I split these up evenly? What's an equation which represents a situation? Well, we can do that. 2x is equal to 10, right? And the solution to that is a natural number. Okay, an extension of this, we were talking about integers before, like whole numbers. We also have sets that represent that, right? This is the set of integers, right? So integers are, you can describe them as whole numbers. So like -3, -2, -1. 0 is an integer. I'm running out of room because of these drawings, right? And so on and so forth, okay? So these are all our integers there, right? You can have positive integers, which is just the positive set, or you can have negative integers, which is the negative set of numbers, yeah? So far, so good. So at this point in time, it seems like you've got all the numbers you need. Like, you know, you can count things, we have whole number things. It doesn't really make sense to need any other kind of numbers until you change situations, right? Let's say you have John and Betty here, but what happened? Let's add in a third person. I think they added in a dog.
Yeah. Just give dogs cookies.
Okay. Shouldn't give dogs cookies, is that right? Yeah.
And
So how does this change our equation? What's it going?
People for 3 things to divide by.
Yeah, so what does that create? That creates 3x is equal to 10. And so you may be thinking, well, I don't know any whole numbers or integers that work for this, right? I don't know any numbers where I multiply by 3 and you get to 10. So the very easy kind of response to that, well, is it's impossible. You can't do it, right? But we take it for granted, but you know, we know how to write this now. It's just 10 on 3, it's just a fraction, yeah? But we take that for granted. We say that, you know, initially, it doesn't make sense to think about things in terms of values like that. We have something that describes that. Do we know how to describe these kinds of numbers? That can be expressed as fractions? They can be decimal. What is it? That's like 3.33
Is it like a decimal?
reoccurring.
Oh, it's like...
They're called the rationals, right? Anything you can express as a fraction, right, in the form P on Q, we can describe as rationals. So where's the set notation for this?
are these symbols important for us to know?
In some sense, yeah. So we use Q for this to represent this. And all the rational numbers, right, we can describe them as P on Q. And there's a condition that P and Q, I'm going to use this notation that means is an element of, or like is a part of the integers, right? So P and Q have to be integers, and so any rational number can be expressed as P and Q, okay? All right, where is this all kind of fitting in? Well, there's two ways you can think about where these numbers fit in. You can think about them as fitting in on your number line, right? Right, there's our, our integers all the way going across. And so where do these rational numbers kind of fit in? In between them, right? So we say, okay, well, yeah, half, right over here. Or you could say 3 and 2 over here, right? So it actually turns out, like initially when you draw your number line, it seems like you've got all the numbers there. There's actually stuff in between that. So far, so good. It seems like we've got everything we need. Do we?
Apparently not.
Probably not. Let me give you a problem, right? What if now I give you something like this? Here's a square. And I say I want this square to have an area of 2 square meters. The question is, what is the side length of this? So we have a value, the square root of 2, which again, where does that actually fit into all of these? Square root of 2 is not a natural number, it's not a counting number. You don't go 1, square root of 2, 2, right? It's not something that just fits in there naturally. It's actually not also a rational number. You can't express that as a fraction. Yeah, right. So can you start to see the problem with like your initial definition of numbers? Like we have numbers that we start off with, which kind of makes sense. But then every time a situation pops up, it seems to appear that like this kind of problem is impossible. Like you could try numbers that get really close if you want to express as a fraction, right? But you won't be able to find a value that works. Ironically, it was Pythagoras who strongly believed that these types of numbers don't exist, that every number should be expressed as a fraction. Why do I say ironically? Well, because a very easy way to see that rationals should exist is because of his theorem, right? If you have your Pythagorean triangle, not your Pythagorean triangle, one of the common like exact value triangles, right? And you find this, you see that, yeah, this is the square root of 2. And you're right, man, like this is the square root of 2 here, again, right? But we take that for granted. We just think that, yeah, the square root of 2 is something that exists, and so we can just put it in there, right? But a long time ago, that wasn't the case, right? Again, where do your irrational numbers fit into this number line? Well, it turns out, right, like we can't completely fill this line with just rational numbers. They fit in, again, somewhere in between. Like the square root of 2 is roughly in between the in-betweens, exactly right. 1.4, like roughly, right? So at this point, I wouldn't blame you for thinking we've kind of filled everything up, right? If we say that we've got whole numbers, in between them we have these rational numbers, and in between those in-betweens we have the irrational numbers. We've kind of got everything there. All of the numbers here, if I was to represent that as a diagram in terms of where they all fit in, we've got our natural numbers, then we have our like integers all around that. We have our, integers, rational numbers, and all of these numbers are encompassed by something we call real numbers. So these are all real numbers here, okay? Which brings us to our new type of number that I want to introduce to you today. And like I said, right, there's a few ways we can think about where this comes up. We think about numbers that come naturally, and we think about equations. So that's kind of the heart of why we need this. This is the intuition that exists here. If I give you a problem like this, a quadratic equation, x squared plus 1 is equal to 0. And we know how to try and solve equations like this. We try and balance both sides potentially, and we run into this problem, right? What's the problem that we run into? Well, in the past we've said you can't take the square root of a negative number. If you try and do that, you're going to end up with something like this, right? And what happens when you put in your calculator? You get a math, it doesn't work, right? And so I wouldn't blame you for thinking that this doesn't really have any solutions. What's the way around this? And you can draw a parabola, yeah, great. Another way to confirm that this shouldn't work, by the way, right? You draw a parabola out, x squared plus 1. When does that equal to 0? Well, it doesn't, okay? So a few different ways that you can show why this doesn't have any solutions. And I wouldn't blame you for thinking that. Jot that down first, jot some of this down first, and I'll talk about why it actually does.